This is Unit 6G. It deals with transformers. So transformer is basically two coils, a primary coil and a secondary coil, and we have this core here which intensifies the magnetic field. Now, as we know, currents have magnetic fields around them, and if we have an alternating magnetic current, this creates a changing magnetic field. So here we've got this relationship, electrons flowing backwards and forwards, alternating current. We have this constantly changing 50 times a second, and this induces, because field lines are being cut, a voltage here again. Now, because there are more coils, we get a higher voltage. This also means we have less current, which we can see that the electrons here, the color is showing the voltage, traveling further here, so greater current, less current here. Now, the formula that expresses this, obviously the size represents what's going on. So if we have twice the voltage, we must also have twice the number of coils. So here we've got twice the number of coils, twice the voltage. So more coils, more voltage. We can also have a step down transformer. This is a step up transformer where the situation is reversed. So we have fewer coils and we therefore have a lower voltage. So the idea is here again, alternating current creates a changing magnetic field, and that involves field lines being cut and a voltage, or a different voltage if you like, being induced. We also have the slightly unusual case of the isolating transformer, where the number of coils are the same, so you get the same voltage out, and this is really for safety reasons, mainly in situations where water is involved, like a bathroom, and we have shaver sockets, so if there is any water gets into the contact there, it can't become, or it can't take the main voltage. So slightly separate case there. Right, so why bother to change voltage? Well, the clue is here in the middle of the slide. High voltage results in minimal power loss. So we have here our power station that produces about 30,000 volts typically, and we step that up. So this is the transformer we saw just now, to a higher voltage, typically 500,000. Now this is about as high as you can practically get without it flashing to the ground, and then we step that down again to use in the home or for industry. Now we step it down to about 240. That gives you plenty of energy. It's still dangerous, but it's not as dangerous as 500,000 or 30,000 volts will be. So there we have the big picture in the middle there. Now, in terms of expressing this using equations, here we can see P for power, that's energy per time, should be the same going in and going out. Energy cannot be created or destroyed. Transformers are actually very efficient. They're one of the most efficient machines we have, about 99% efficient, mainly because they have no moving parts. So what can we see here? We've got large current going in, relatively small voltage. Going out, we have a much smaller voltage and a large voltage. Now the key formula which I recommend you quote is this one here. Power loss in this case is I squared R. So although these cables are designed to have minimal resistance, they will have some, so there will be some power loss, but the key thing is this squared. So if we double the current, we quadruple the power loss, or to put it another way, if we halve the current, the power loss goes down by a factor of 4. So we want high voltage. It's repackaging the energy in such a way as to minimize power loss, as we said here. So stepping down, as we said earlier, for safety reasons, the situation is reversed. Large voltage, small current, and that results in a relatively large current going into the home.